back. So today we'll continue talking about linear transformations, solutions of system of equations of the form ax equals 0 and ax equals 2b, as well as elementary operations on matrices. Here's a quick reminder of yesterday's lecture of some of the material that we talked about. So the solutions of homogeneous equations on the left. So when we talked about the solutions of homogeneous equations on the left, we talked in particular about the case when ax equals to 0 implies that x is equal to 0. And that implied the following facts: that the every pivot is a column. There is a pivot in every column. Then columns need to be linearly independent. Then rows span all RC. So in this case, matrix A is a linear transformation from RC to RR. Then it necessarily happens that rows span all of RC, and the map is one-to-one as a linear transformation, or as we call it, associated function. So it maps distinct points in RC to distinct points in RR. And of course, it can only happen when C is less or equal than R. And so the number of rows in the matrix should be not greater. So number of columns should not exceed the number of rows. If we have an inhomogeneous equation like here, we can ask when it has solutions for any value of vector b in the right-hand side. And the conclusion was as follows: that there's a pivot in every row, that rows must be linearly independent, columns span all RR, the codomain of the map, and it's an onto map, right? So it hits all points in RR. And all the above conditions in the right column can only happen if number of rows is less or equal to the number of columns. So here you can see clearly there is an interesting interplay between appearance of rows and columns in a complementary fashion. So the pivot in every column for the homogeneous equation implies that there's a pivot in every row in inhomogeneous equation. And of course, if A is a square matrix, so the number of rows is equal to the number of columns, then there's a pivot in every row, if and only if there's a pivot in every column. So these the above two rows, they merge into the same statement. So that is all equivalent. Now let's recall what span linear independence mean. So if you have a collection of d vectors in Rn, they can only span if d is greater or equal than n, and these vectors can only be linearly independent if d is less or equal than n. So let's make a quick recap. There are three vectors, three two-dimensional sources, three vectors with two components each. Are they linearly independent? Well, clearly the answer is no, because there are too many, right? So there are three and there are only two components. So, but just for the sake of the argument, let's put them in the matrix and row reduce them anyway. So we're going to put them in a matrix. So we're going to put them in rows, right? So this is the first vector, this is the second vector, and this is the third vector. Right, so the first step, we swapped the rows, the first and the second row. I mean, of course, the way is not unique. You don't have to do it this way, but it's one of the possibilities. Then we multiply the first row by -1 and add it to the second row. So you get 0, 3, and multiply it by -5 and add it to the third row. So you get 0, 6. And then we get rid of the last row by combining the second and the third rows. So as we discussed, the row operations, they do not affect linear independence of the system. And the final matrix has a 0 row at the bottom. So the original rows, therefore, were not linearly independent, according to the table that we had earlier. So we can see that there is no pivot in every row. The columns that do not span and all other conditions are not satisfied, but the columns are linearly independent, right? So if you look at columns, it's still okay, right? So 0, 1, 0, 0, and minus 1, 3, 0, they are linearly independent. Okay. Now let's take the sort of the complementary case when we have vectors 1, 2, 3, 1, and 1 minus 1, 1, 1, 5, 1, 9, 1, which are 4 component vectors, and there are 3 of them. So we should do the same reduction procedure. So we'll put them like this: 1, 2, 3, 1, 1 minus 1, 1, 1, 5, 1, 9, 1 in rows. So it's a 3 by 4 matrix. Again, you can do it as an exercise. The pivot, we need to find the pivots. So again, it's just to reduce the complexity of operations, it's easier to swap first 2 rows. After you do that, you isolated the first pivot column, then the second pivot column, and the last one. So there's a free variable, and so the final echelon matrix has no 0 row. So the original rows are linearly independent. Here's a summary slide again. Now, we've been exploring various facets of linear algebra. Sort of this illustration kind of summarizes how the exploration process goes. You know, when you start from a corner, you can only see some part of the story, and sometimes your first impression is not exactly representative, as you can see here. And then only after you spend some time understanding what's going on, you can actually see that there is an elephant in the room. Let's talk about operations with matrices, and then we'll. So you may be familiar with some of them already, so we just have them here to summarize the story. So just like vectors, multiplying the matrix by a scalar typically means that you multiply every element of the matrix by that scalar. So 3 times this square matrix gives you the matrix on the right. -2 multiplied by this 2 by 3 matrix gives you matrix over there. And of course, if you multiply everything by 0, you get a 0 matrix. We are allowed to add matrices only of the same size, right? You just add them term by term. So these are matrices of the same size. We can add them. These are matrices of the same size. We can add them. And of course, adding also includes subtracting and multiplying by numbers or any linear combination of these matrices. But these matrices are not okay because there is no meaningful way to assign a matrix which is the sum of these two. An important operation is called transposition. So the transpose of the matrix is what you get by reflecting along a northwest-southeast diagonal. Sometimes it's called the main diagonal. Right? So it takes the old first column and makes it the new first row, etc. Right, so here's an example. We have a diagonal like that, right? And then after reflection, the row becomes column and the column becomes row. So the 2, 4 was the first row, now it becomes the first column, and so on. So clearly this operation converts n times, if A was the n times m matrix, then A transposed, so it's denoted with this letter T in the superscript, that A transpose has size m times n. Transposition of a vector column is a row. And of course, just transposition of a square matrix is again a square matrix. And in this example, this matrix is symmetric, right? So it does not change under the transposition. You can also say that in this matrices, if you have Aij is the matrix element of the matrix, then Aij transposed is equal to Aji. So here's a bit more on this. So if you can write M or A, you can pick your favorite letter. The matrix and Mij would denote that M with indices I and j denote the entry in the ith row and j's column of the matrix. So in this example, A11 is 3, and A23 is equal to 8. So this is second row, third column. Now let's talk about matrix multiplication. Say we are given two matrices, A and B. If A has as many columns as B has rows, then we can define the matrix product or the matrix multiplication in this precise order, A times B. And the matrix product is determined by the formula. So the ijth element in the product of the matrices is given by the sum of the AI1 times B1j, AI1 times 1j plus AI2 times B2j, and so on times EIN times B and j. So here this is since the A has as many columns and B has rows, we can write such a formula. So let's look at this in a bit more detail. Now, so AB has as many rows as A and as many columns as B. So this is how multiplication is set up. So here is an example. We have a matrix 3 by 4, 3 rows, 4 columns, and we multiply it by the matrix which has 4 rows, and in this case, 2 columns. Right, so number of columns in the second matrix does not really affect, I mean, it will define you the number of columns in the resulting matrix, and then, so the resulting matrix will have two columns and 3 rows. So you can think of it this way, that this number got eaten up, right? So since you multiply the first row by the first column, and then take a sum. So this what remains in the end is the number of rows in the first matrix and number of columns in the second matrix. Let's calculate. So remember, the formula goes like this: you take so let's evaluate this number, which is AB11. So according to the formula from the previous slide, we need to take A11 times B11 plus A12 times B21 plus A13 times B31, and then plus A14 times B41. So in other words, you multiply 1 plus 1, so it's 1 times 1, plus 2 times 2, plus 1 times 1, plus 2 times 0, and so on. So that's here you calculate the first element, and then you calculate all the other elements. So I have prepared here the calculation. So the first answer will be equal to 6, right? So this formula that I just wrote, you take what I showed in blue, the first row, and then you multiply it by the first column. And this is the calculation, so that you get 6. Then let's calculate the next element. We take the second row of the of matrix A and multiply it by the first column of matrix B. In this example, we get 0. Then we do third row and first column, we get 8. And then do the same with the second row, with the second column of the matrix B. So we have first row of A times second column of B. This is the calculation, we get 10. And then we just keep going. Here we have 11 and 6. You can check it by yourself. So another way to see this is that, indeed, so we can have a matrix B, we should think of as a row of columns, right? So remember, it's a list, right? So my matrix is a list of vectors. So if matrix B is represented as a list of vectors, B1 through Bn, then the product of matrices A and B can be thought of a list of all products of matrix A by each of the vectors in that list, right? So you get, in the first column, we have vector AB1, second column, we have vector AB2, etc. And in the last column, we have vector A times Bn. Of course, the previous example, the previous lecture material, when we only looked at matrix vector product, is a special case. So here we're just simply taking that rule and then applying it to every column of the matrix. Okay. So here's an exercise. Of course, there are exercises in homework. If you need more examples, you can try this yourself. You can pause the video while you do the calculations. Okay. Now, matrix multiplication has the following properties. So the product is associative, right? Meaning that we can multiply, we can put parentheses in different orders. So that ABC is equal to A times BC. It distributes over matrix addition, right? So you can write it as A times B plus C is equal to AB plus AC, and this happens no matter in which direction you multiply. So if you multiply it B plus C on the left, you'll get the same sort of formula, but in general, it's not commutative, right? So indeed, if you look at the dimensions of A and B, then often matrix AB makes sense, but BA does not, right? As we had in one previous example. And even if this is the case, for example, when you have square matrices, then of course you can multiply AB and BA. Both products make sense, but otherwise, if you have done an exercise on the previous slide with the two square matrices, you see that this is not the case. Right? So here we can have again two examples. Now it's a matrix 2 by 2 times 2 by 3, and 3 by 2 by 3 times 3 by 3. Again, do the calculation yourself while pausing the video, and the answer will appear on the next slide. Here are the answers. So notice here that the matrices did not change. So if this was matrix B, this is also matrix B, and this was matrix A, this is also matrix A. Now, as we denoted last time, you can say this is the identity matrix 1. You can, if you want, you can put a subscript 2 or 2 by 2. And this is also a 3-dimensional 3 by 3 identity matrix. So this is an identity. You can multiply it from any side whenever the multiplication is well defined, and it will get you the same matrix. So you can put it as 1n or in. it's the matrix with 1 along the diagonal and zeros everywhere else. So 1 by 1 matrix is just a number, I2 is 1, 0, 0, 1, and so on. So it's an identity for matrix multiplication whenever the multiplication is well defined, and from both sides. Note that the identity matrix is the unique reduced echelon and by n matrix, which obviously has pivot in every row and equivalently in every column. Okay, the same number of rows and columns. Okay, so here are some more examples. So you can try it by you can try it by yourself. So now we have well, I mean the first matrix in this. My first matrices in this product, they have a lot of zeros, but not all of them are zeros. Right? So do the calculations. Here's what the answers are. You can check yourself. Yes. Now let's talk about elementary row operations. So we can do elementary row operation, meaning that adding rows, multiplying by some numbers, and taking linear combinations. So by multiplying on the left to this matrix by the matrix, which is obtained by performing that row operation on the identity matrix. So let's look at an example. Well, we can have this. First of all, let's first do this calculation by yourself, and then later we'll discuss what is the meaning of the matrix A and matrix B in this case. So it turns out that after you do this multiplication, you get identity matrix in both examples, right? So if this is matrix A, this matrix is B, and the answer is 1 or I, right? So we can call that B is the matrix which is inverse of A. That will appear on the next slide. So we say that the matrix A is invertible if there is some other matrix B such that B times A and A times B are both identity matrices. And in this case, we call B is the inverse of A. So it's crucial that this has to be satisfied in both orders. Right? So that assumes that the matrix has to be quadratic. It has to have the same number of rows and columns. Then the inverse is unique if it exists. It's easy to check, right? So if there are two inverses, and then you should by using standard algebra techniques, you can show that the inverse if B and C are two different inverses, then from the associativity, it inevitably follows that B is equal to C. Is the identity matrix invertible? Sure, right? You multiply it by itself, you get the matrix, you get it back, which means that the identity matrix is the inverse of itself. Okay, now, if A is the invertible matrix, then we can write A is, so the inhomogeneous equation for X, you can formally solve like by inverting matrix A. So if A times X is equal to B, now we can multiply this by A inverse, right? And A times A inverse is equal to 1. And on the right, we get A inverse times B. So if Ax equals to 0 has only 0 solution, then of course we say that X is equal to A inverse is equal to 0, which means that the matrix A has to be invertible. Okay, so here's again the summary from earlier. we can look at this again. So remember, we can add here a row that if x equals 0 is a homogeneous solution, that it has to be a one-to-one map. And if x is a solution of the inhomogeneous equation for any value of b, it has to be an onto map. So let's see how the inversion goes in more detail. So we should be able to know how to calculate the inverse matrix for every matrix A if it's invertible. So if it's invertible, then as we discussed, then it's a square. And all the conditions on the previous slide, which we just showed, hold. We talked about this. And then, so if you have a square matrix, being invertible is equivalent that being invertible for a matrix is equivalent to one of these conditions. So row reducing an invertible matrix, row reducing an invertible matrix to reduced row echelon form gives an identity matrix. Because remember, so that if you have matrix A, then it's pivot. There must be pivot in every column, every row, which is other way to say that this is an identity matrix. And we can use this fact to calculate the inverse of a matrix. So if you use row reduction, which is implemented by elementary matrices, so if M is invertible, then we can row reduce it to the identity, and then we can, the steps that we use to do the row reduction will allow us to calculate the inverse matrix. Here's how it's come about. So there exists some elementary matrices, E1 through EK, for some value of k, such that if you multiply with these matrices on the left in this order, E1, E2, and so on, k, we'll get the identity matrix. And then if you multiply by M inverse on both sides, we'll get that M inverse is equal to EK times EK minus 1, and so on, times E2 times E1. So these equations are equivalent, and we can combine them together. So we can put the matrices M and I next to each other in one big matrix of size n by 2n, and so we can define a new matrix this way, which is over here. And then if this matrix has n rows, and therefore it can be multiplied by square and by n matrices, which are those matrices E1 through EK. So we know that the first equation multiplied by M gives us identity matrix, and the second equation will give us the inverse. So in other words, we will be doing the echelon, we'll be reducing to the echelon form the rectangular n by 2n matrix M slash M slash I. Okay. So what those matrices EI do? So they show row operations, right? So this is our goal. Yeah. So in other words, we can obtain one matrix from the other by row reduction. So to find the inverse, we first write it like this: row reduce it, and then we identify the inverse matrix in the second half. And if it's impossible, if somehow it doesn't work, then M is not invertible, so it doesn't have enough pivots. Okay, so let's find the inverse of matrix 1, 2, 1, 3. Right, so we put it next to the identity matrix like this, so it's a matrix 2 by 4. And now we'll do the row reduction. So here's the matrix again. We know how to do the pivot form, so we do we can subtract the first row from the second row, and then we get rid of the pivots. So we just and then we reduce it to we make it to the reduced pivot form. So we have 1, 0, 0, 1. So this is the identity matrix. And the first matrix, and over here we have matrix M inverse. Okay. So that's the inverse, and we can check that this is indeed an inverse. So the inverse matrix of 1, 2, 1, 3 is 3 minus 2 minus 1, 1. Okay, so then do these exercises by yourself. Do the inverse matrices for 1, 2, 3, 7, 1, 2, 3, 6. Yet another way to think of calculating the inverse is to apply the another way to think about the inverse is to look at columns of matrix A to the minus 1, right? So A inverse, the columns of this matrix are A inverse acting on E1, E2, and so on En, where En, E vectors, E are the vectors of the standard or canonical basis in Rn. So these are solutions of equations Ax equals E1, Ax equals E2, and so on. And to find the solutions, we would row reduce the augmented matrices, right, which have matrix A on the left, and then the vectors from the standard basis on the right. We can do them all at once by looking at this big matrix, A with E1, E2, E3, and En. And of course, we know that this is the same as the identity matrix. So now consider arbitrary matrix with coefficients A, B, C, and D. We do, let's do this, the same procedure. So we multiply the second row by first row by, yes, first we normalize, we divide by A, assuming that A is not equal to 0. Then we subtract the first row times C from the second row. Then we divide again by the coefficient D minus CB over A to get 1 over here, and then we make it a pivot form. So and then we need to collect what's an N, so that will be the inverse of this matrix A, B, C, and D. So now the following statements should not be equal, the following combination should not be equal to 0 for this to happen. So if AD minus BC is not 0, then the inverse is given by the following formula, where this quantity is called the discriminant or determinant. So we'll talk about this later. So basically, we have here what you need to do. A and D, they switch places, and B and C, they acquire minus sign, and then you need to define by AD minus BC. Okay, so that's it for the inversion. So we'll continue in the next video.